we've had a bit of time this morning to have a go at this problem using Thevenins and an AC network. Okay, and yes, the maths is more tricky because we got complex values, but if you follow the process as we've always done before to find the Thevenins voltage and current, it's not particularly difficult. Just requires you to be able to easily use both polar and rectangular forms of these numbers. So what we're asking here, and we'll go through and check this out for the first load, and then I can leave you to at your leisure to the 8 minus 2J. So we've got a circuit here that's got a resistor, inductor and a capacitor in series, and then a load is connected across the capacitor. So first thing in Thevenins is, gents, to make an open circuit. Take your load that you're interested in out. So the circuit looks like that. We've always had this convention where I'm just going to make that a little smaller. So I've got a bit of space for this convention where we label those two terminals A and B, and this open circuit voltage here is a Thevenins voltage. I'm going to call it E Thevenins in this case, E little t. So the first part of our calculation is all towards finding the open circuit voltage, which in this case is the voltage across the capacitor under open circuit conditions. So yes, we could find the voltage across R or the voltage across XL, but that's not what we need. Everything we do now is tailored towards finding voltage across the capacitor, because that's all we need from it. So where do we start with that? Most of you have done this, so what did you do? Yeah, impedance. We find Z, and I'm going to give it big T. We mustn't confuse this with Z little t that we're eventually going to find, the Thevenins impedance. This is purely to find the current. That equals, what's the formula for it? Yeah, okay, in that form you've got ZR plus ZL plus ZC, all those impedances added together. So we got 6 for the resistance plus, and then these two go together because they've both got J associated with them. So when we looked at this last week, we opened a set of brackets and we said that was XL minus XC J, didn't we? Yeah, and that's in ohms. Yeah, capacitance is a minus 90 degrees or minus J. Inductance is positive 90 degrees or a positive J term. Yeah. Which then all added together is 6 plus 5 J ohms. Okay, and that's probably worthwhile at that point, in case you need it in polar form later, as just to convert it as well. So what was that in polar form, gents? One of you must have it. Ohms, angle. Yeah. Now, just look at that. We've got a positive angle. we've got both inductors and capacitors in the circuit. Right, but is this circuit overall inductive or overall capacitive in nature? Inductive. That's got a positive angle associated with its total impedance. So overall, that source, the generator or whatever it is that's given us 100 volts, is seeing an inductive load, despite the fact there's some capacitance in there. Yep. So, having calculated our impedance, what can we do next? Work out your circuit current. Now, there are two ways we could do that. We could either, we've got a voltage here, you could use polar form or you could use rectangular form. That's 100 plus 0J or 100 angle 0. So which is the easiest to do at this stage? 100 angle 0, because we want to do division, so we might as well use that converted value and the 100 angles. So I is equal to E over ZT. That's 100 angle 0 degrees over 7.81 angle 39.8 degrees. How do we do that, Jack? Take the angles away. So the result is, Jack, yep. Does that fit in with the word civil? Remembering, what did we say this circuit is overall? It's inductive. We've got a current that's lagging the voltage by 39.8 degrees. Inductive circuits, currents after or lagging the voltage. Always worthwhile. Do that check. Does it look right? Yeah. So now we've got a current. What can we find now? We now know this. So can we find VC? Yeah, because we can do I times XC, can't we? Yeah. So E little t, the Thevenins voltage, is equal to VC, which is equal to I times XC. I is our 12.8 angle minus 39.8. I'm going to multiply that by, we got minus 3J. So what's the XC in polar form? Capacitor, what's the angle associated with it? Minus 90 degrees. So we got 3 angle minus 90 degrees. We do that multiplying out. .4 volts, angle 130 degrees. Yeah. That's our Thevenins voltage. 38.4 angle 130. Yeah. So the next step in the Thevenins process is to calculate the impedance looking in, and that impedance then is the Thevenins impedance that we need for the circuit. So what have we got there? We've got a capacitor, an inductor. How are they connected? Yeah, the resistance and the inductor are in series with each other, and that series part is in parallel with the capacitor. Yeah. So what's the best way to tackle this then? Okay, yeah. So you found, so did you convert the R and XL to polar form? No? You did it all in rectangular. Yeah. So Z-T, that is, the top line is 6 plus 8J times minus 3J. Yeah, you done that, did you? Then underneath, that's these three added together, which we've already done, haven't we? Already done that in the previous calc, all those three added together. That was 6 plus 5J, wasn't it? Agreed? Yeah? So you might do it again, but you already had it. It's worthwhile remembering that you've already done something. Multiply that top line out, becomes (24) minus 18J over 6 plus 5J. What do we have to do now to do that rectangular quotient? Yeah. Yeah. So multiplied by the complex conjugate. Yeah. Language for it. Or the mathematician's language for it. So it now equals 24 minus 18J times 6 minus 5J all over 6 plus 5J times 6 minus 5J. What of this bottom multiplication out? What is that always? Always end. Why do we do this multiplied by complex conjugate? Gets rid of the J term. If you remember, what does it always end up? Yeah, the two numbers squared and added together. So a 6 squared plus 5 squared. I think that makes 61. Yeah. Yeah. So the top end, what does that multiply out to? Anyone got it in front of them? Everyone agree with that? And when you divide it out, what does it equal? (0.89) minus 3.74J. And the units of that are ohms. Okay? Converted to polar, that is Okay, 3.84 ohms minus 76.6 degrees. We now have both the two values, E little t, Thevenin voltage, and Z little t, Thevenin's impedance. So we can put those and we can put our load back. So gents, what the value of the load A was. So for A, this load was 10 plus 3J. And what was this Z in rectangular form? 0.8 something, went up. Minus 3.74 J. Because it's going to be easier to add those two together in rectangular form, convert afterwards, find the current. So what we're looking for now is just simply do the total impedance of this circuit, 0.89 minus 3.74 J, and add that to 10 plus 3J. I'm sure someone's done it. That comes out to, must be 10.89 minus 0.74 J ohms. Converted to polar, that is you've done yours without adding those together. 10.9 ohms degrees. Yeah. So now we've calculated the total impedance, and remember we can now put any load in there. 9 minus 6J. This bit to the left of those two terminals A and B will act exactly like the original network of a resistor, inductor and capacitor in every way, unless we change the frequency. You must remember that. Okay, so to finish off for the answer to A, get rid of that. Finish off to get the answer to A, we need to do IL, the load current is E Thevenins over this new total impedance, that is 38.4 angle minus 129.9 over 10.9 angle minus 3.68, to which we get a final answer of, who's got it, 3.5 amps (126 degrees) will do me. Okay, I'm going to go through the other load step by job. Okay. Have I